I'm Konstantin Lignos from Brandeis University, and today I'll be talking to you about effective architectures for low-resource multilingual named entity transliteration. And this is joint work with Molly Moran, also from Brandeis University. So an overview of our talk today. First, this is an intentionally short and sweet summary of our work because we think remote talks should be on the short side. Our research question is what machine translation architectures give the best results for named entity transliteration? And to answer this question, we're going to follow up on a study by Wu and Yarowski from 2018, who created a corpus of name transliterations from aligned versions of the Bible covering 591 languages. So we experiment with training a single model for transliterating names from 590 languages into English. We're training in total on about 280,000 name pairs. Now, across languages, the number of training examples varies quite a bit. So the median is 454 examples, but that ranges from 34 to 938. So we can have, in some cases, very few shot name transliteration. So we're following up on some preliminary experiments that Wu and Yarowski reported from multilingual transliteration using OpenNMT. Now, the models we train are not in any way unique or novel. We're just taking pairs of encoders and decoders and asking how they perform. So the encoders we're looking at are GRU, LSTM, BiLSTM, and Transformer. And then for the decoder, we have OpenNMT's default decoder, which is an LSTM with attention, and the transformer decoder. And so we'll often just call the pairing of the transformer encoder and transformer decoder just the transformer model. Now for evaluation, we're going to use three different metrics. One is exact match accuracy. So was every single character of this name transliterated correctly? Character error rate, which is a normalized error rate of how many characters were incorrect, and then the fuzziness in top one mean character F1 metric, which was developed as a part of a named entity workshop transliteration share task in 2018, and that's the metric we'll focus on the most. So each configuration of encoder decoder, we trained it 10 times with 10 random seeds and evaluated on a fixed 80-10-10 train dev test split that matches what Wu and Yarowski used. Each training example contains a language flag token that specifies the source language. So if we were transliterating Constantine, it would look like this, and then we would have what the source language is in brackets there. So here is a really simple summary of what our performance looks like. The transformer wins. You can look at all the different encoder and decoder combinations. What you'll see consistently is that for each encoder, adding the transformer as the decoder as opposed to the default decoder improves performance. You can see that the GRU does quite poorly with the default encoder, but is improved quite a bit by the transformer decoder. And just digging into the numbers a little bit here, you can see on the left results for the standard decoder, and on the right using the transformer decoder. And some patterns. First, the GRU, as I said, improves quite a bit when you pair it with the transformer. So you see the mean F score goes from 92.2 to 92.8. One thing that we were kind of surprised is that using a BiLSTM as the encoder as opposed to just a unidirectional LSTM doesn't help at all. In fact, it slightly reduces performance, which was surprising to us. And finally, when you use the transformer as the encoder and decoder, not only do you get the highest mean scores, but a substantially lower standard deviation, which was surprising to us given the transformer has quite a bit more parameters. It might not necessarily predict. It would also show reduced standard deviation, but it does. So it's really just a win in every dimension except for training time, in which case it's about 3 times slower than everything else. So we've told you, so we've got a nice high-performing kind of off-the-shelf system. One thing you might ask is, well, can you improve that? Because obviously if you just take an off-the-shelf setup, it's a little boring. So what can we do to help? Well, we didn't find anything that helps. We did find things that don't help. So for example, one thing we thought about was using macro language tokens, and these specify some sort of higher level language family. So rather than just having, as on the standard line here, the specific language token, you might say, hey, this is the language, but also here is a larger language family that this language is a part of. So it didn't help performance, it slightly hurt it. And one of the potential reasons is out of the 590 languages we were using as source languages, only 36 of them had macro languages defined. So it's not just an issue that they didn't help anything else, but those 36 got better. In fact, those 36 got substantially worse. So basically, I think these macro language tokens just amounted to noise in the training data. Now, pre-Romanization using URoman, which is a universal Romanizer, also doesn't improve performance. So by trying to force as many scripts as possible into Romanization, it doesn't really make the task of transliteration any easier. So basically, anything that these tricks might have sort of taught the model, it seems like it figures it out on its own much better. Now, one thing that we'd love to give you a great answer for is, okay, well, kind of why do you need a transformer for this? So many people, when they look at transliteration, especially if they come from a machine translation background, they say, look, this is just a easy version of machine translation. There's basically, very limited, if any, reordering. So why would you need a transformer for it? What's the real benefit here? And the short answer is we don't have a good answer to that. But what we can tell you is that there isn't a really good path to an answer, in our opinion. So one thing that reviewers encourage us to do is basically add anecdotes to this paper by looking at examples and trying to spot patterns. But there's a serious issue with that. This work involves transliteration from 590 languages, and the vast majority of them are written in scripts we can't even read as authors, nor could we feasibly get speakers to do a manual analysis for that many scripts. And so if we were to do an error analysis that only covers what we can read, it really wouldn't do the multilinguality of this work justice. So we're not going to take that approach. We're not going to give you anecdotes based on just what we see in the data because we can't read most of the data. And some folks also suggested some, things that would appear to be obvious ideas, like why don't you just categorize all the languages by scripts? So first of all, categorizing languages by scripts isn't nearly as obvious as it seems. There's lots of variation, even within languages that are potentially using what you might call the same script, even though identifying what a script is the same is a little bit tricky. And even within Latin alphabets, there's a tremendous difference due to diacritics, for example, between languages that we might all categorize as Latin. So you can do this categorization. We don't think it's irresponsible. We just don't think it's nearly as informative as people think it might be. So what can we do? So one thing we did is look at what the per language average performance looks like and what we can try to correlate that with. So we're going to look at two plots here, and what they're showing is for each language the mean character error rate across all items in the test set. So first, we're looking at the number of training pairs in the language, and we see, due to the fact that there is pretty successful transfer learning here, that while there certainly is a correlation, that the more training pairs you have in a language, on average, the better the performance is, it's not a very robust correlation, and there's a tremendous amount of variation. So in the most common cluster here, where you have about 500 training pairs per language, the character error rate ranges from near 0 to almost 50. So we wondered if there might be an easier way to explain this variation. And one way we could is by looking at mean edit distance to English. So here we see, again, not a perfect correlation, but at least a much less noisy correlation. And this is not surprising. Basically, on average, if the number of edit operations to turn the source string into the target string is higher, the performance is worse. And so while this is not revolutionary, at least this provides kind of a more clear explanation of what's going on. Now, to dig a little bit deeper into this, we actually trained a statistical model using logistical regression to perform error analysis on the test set. So specifically, we trained it to predict whether a pair would be correctly transliterated by the LSTM transformer and transformer models. So both are using the transformer as a decoder, but they vary on whether they're using the transformer as the encoder. And we're interested in that because we see a big increase in performance using the using the transformer as the encoder. So the predictors in this model were the number of each type of edit, so insertion, deletion, and substitution between the source and target. And we modeled in total almost 700,000 predictions. That's because we have a moderately large test set and 10 seeds per model and 2 models here. And basically the error model suggests that both transliteration models that we evaluated handle deletions equally well, but the transformer handles insertions and substitutions a little bit better. And there's a slightly larger advantage with regards to substitutions. And since basically any transliteration from a non-Latin alphabet to English is going to be 100% substitutions, that's critical. So some takeaways from our work. First of all, if you want the highest performance of this task, use the transformer as the encoder and the decoder. But if you don't need the very highest performance, if you can settle for second best, consider using an LSTM, not a bi-LSTM because it doesn't help, as the encoder, and then for the use transformer as the decoder, and that will train in 1/3 of the time of using the transformer as the encoder and perform almost as well. But there's a lot more work that remains to be done here to improve our models and explain why the transformer does so much better. There are also a lot of questions to explore in data processing, such as Unicode normalization, which could, for example, turn a single code point, which represents a character with diacritics, into multiple code points, which separately represent the character and the diacritics. So what works best there? We'll just need to do further experiments to find out. And our future plans include evaluating in target languages other than English, which we had to do basically just to cut down on the computation time here, and hopefully evaluating transliterating all languages to all languages. So thank you very much. This has just been a short talk with just the highlights, but if you want more information, please check out my website at lignos.org. Thanks.